is actually to take a subject area and see what technologies, what new things that are being spun out of it, are being created as part of it. And you may remember, as we spoke about a little bit earlier, that one of the biggest things about deep space mining, about off-Earth mining, is not just the mining bit, but it's actually all the applications that we might get out of it for problems on Earth. And maybe that is how we can help fund the exploration, the innovation that we want to achieve. So that's really the next 2 sessions, and I think it's a bit of a payoff. So well done for getting this far in the conference, and we've got hopefully some very exciting presentations, starting with Professor, Doctor?
Either one.
Either one. Professor Dr. Leslie Gertsch, who's come from Missouri University of Science and Technology. Leslie was talking to me earlier, and she was saying that one of the really important things about mining is the fact that it's very much about a process. Come out here, Leslie. Let's see. Let's take a look at you. You've come all the way here. You've come all the way here from the US to talk a little bit about what your work is showing us. Take it away.
All right. Cool. Thank you. Well, as he said, I'm Leslie Gertsch. I'm from Missouri University of Science and Technology, which was at one time the Missouri School of Mines. I've taught at the Michigan School of Mines and Colorado School of Mines. So yes, mining is the sort of thing I look at. My background is rock mechanics, which of course applies to things besides mining, but we're looking today at the rock mechanics of space, which is something that we haven't really thought about before, at least I hadn't too much, with respect to potential space mining methods. Now, after a beginning, we'll go into rock mechanics in the space environment, how mineral deposits are formed, because rock mechanics plays a part in that, and terrestrial mining methods a bit, and a few of the many potential off-Earth mining methods that have been proposed, and the summary with a few little things, nuggets that I hope to leave you with at the end to get you thinking along these lines. How it all started, I'm not going to go over this in great and glorious detail, but just remind everyone that rocks are solids, and they have been in existence in some form or another, solids that is, since roughly the last 13.7 billion years, or 1,000 million. And the solar system itself, though, is much younger than that. It's less than 5 billion years old. And the Earth-Moon pair, of course, is even, especially the Moon, is slightly younger even than that. So I wanted to go back and point out something that many of my introductory geology students don't always like to have to learn, is that if you're going to mine something, you have to know something about the material you're mining, and that's rock. In the solar system, and probably more widely even than that, things that aren't stars are solids. And there are 2 very general categories, the primitive bodies and the differentiated bodies. Now, after the supernova shock that went through this cloud of material pre-solar system, and it basically started the material clumping together into ever larger bodies. Some of them never got large enough to melt, and those are primitive bodies, and they form a significant proportion of today's asteroids, or at least pieces of today's asteroids. But differentiated bodies did melt because they got big enough and had enough radioactive heat sources, generally aluminum-26, and were large enough that their heat loss was slowed enough that their material melted and differentiated according to density. And that's how we get planets. So the planets are differentiated, and many of the asteroids are also differentiated. So we get different materials from their cores, their mantles, and their crusts, to be very general about it. So those are today's planets and large moons. So all of these are potential targets for mining. And the mechanics, the rock mechanics, have already come in at this point, and we're only a few slides in. So what is rock mechanics? It's understanding and predicting the response of rock to disturbances, whether they're artificial or natural, due to chemical, thermal, mechanical, biological, etc. causes. Generally, here on Earth, in the mining business, we talk about rock mechanics in the senses of controlling fragmentation, either by explosive or mechanical means, and also maintaining our ground stability, ground control. Now, I'm using it here in this talk in the very general sense as the mechanics of natural solids, which in that definition includes the intact rock, the fractured rock, and regolith, which you could consider ultimately fractured rock. It also could include volatiles, or materials that are volatiles on Earth, that are solids generally elsewhere. Oops, let me go back. There we go. For example, the fragmentation part, this is from a project I did a few years ago on blasting asteroids, when I was still thinking of most asteroids as more or less solid bodies. Now we know that many of them are rubble piles, so it's just a little bit different. But for those solid bodies, there are many different ways we can fragment them, and this was an approach looking at some blasting patterns, not quite to the level of delays, but just general patterns for drilling that may or may not be useful in changing the size and the mass distribution of an asteroid that's on a threatening path towards Earth. And oh, by the way, we could also get some material that we can use for other things, which is the core concept of ISRU, that wonderful NASA term for space resources and mining. There's also mechanical fragmentation. Now, notice I've been talking about asteroids, but as I go through here, I'll be talking about Mars and the Moon and some other bodies as well. People ask me, oh, what's your favorite thing to mine from? And I don't really care. I'll mine anywhere. It doesn't matter. So mechanical fragmentation, this is from a slide that was just talking about some of the various different ways of breaking up rock that don't have to do necessarily with explosives. And the diagrams on the right are just mostly several different ways of, unusual ways, I should say, of drilling rock. Most of them are not energy efficient, but a lot of times energy efficiency is not really what you want. Something else may be more important for that particular project. And I wanted to put the picture of the cold planer in there. Let's see here. So because so many people have seen it, but don't think of it as a mining machine. But, and this is a bit of a comment on one slide in our previous presentation before the T, and that, I'm sorry, I forget who the author was, but said that there would be no mining equipment. The equipment you use to mine is, by definition, mining equipment. It may not be excavation equipment the way we normally think of it, but it's still mining equipment. So we need to bear that in mind, just because we get into habits. Regolith, this is the broken up rock. On planets, it occurs from weathering, including some impacts. But here on Earth, where we're most familiar, the weathering tends to be with some of the things we were hearing in the last hour, the rain, oxygen and such. It's affected by life, and we've come to be accustomed to interpreting this often in subverbal ways even. On asteroids, there is still weathering. On the Moon, there is weathering. On Mars and on some of the other bodies in the solar system, there is weathering. But it's different types of weathering, different processes with different results. Some of those results may produce deposits that we could be interested in exploiting. So the thing about regolith versus solid rock is you have to deal with more granular mechanics, which is kind of tough because sometimes grains can actually behave more as fluids, sometimes more as solids. And I wanted to put up these pictures of some of the parts of the surface of asteroid Itokawa, to show you what some scientists would actually call dust. Now you notice the scale bars there at the bottom, or within each of those 6 images. They range from 1 meter to 10 meters. Those are pretty good sized boulders, and nothing against those particular fields of science that call them dust. They have very good reasons for doing so in their field. For us, that's not dust, but we have to deal with it anyway. So whatever you call it, doesn't matter as long as you know what it is. And we'll also be dealing with water as rock elsewhere in the solar system. Basically, where we're in conditions of differing pressure and temperature from what we're used to on Earth. Here we've got a diagram, just a phase diagram with the nitrogen and methane and water boundaries. And also here along the left side, some of the places in the solar system where the surface of these bodies will mean that in some places there's a methane triple point in some conditions there. On Earth, we are near the triple point of water, and Mars isn't all that far away from it. And nitrogen, we've got Triton, the largest moon of Saturn. Its surface is near the methane triple point. And it's got a hydrocarbon cycle similar to our water cycle. And we see some methane rivers there, or a river system. On the right, we've got an image, the orange image is from Huygens lander on Titan, and it's shown at the same scale to the image on the right from the moon. So we can see we've got some actual cobbles here, good-sized cobbles, maybe a few small boulders in the distance, in addition to some fines. Maybe not as fine as what we see on the moon. But this is the stuff we're going to have to deal with if we're going to be dealing with solid materials. Triton, which is the main moon of Neptune, its surface is near the nitrogen triple point. It's geologically active. You've got volcanism, ice tectonics. These black streaks here seem to be some sort of eruption product, and since they seem to be more or less parallel, there must be some sort of wind process, and this all could possibly tie in with it, but we've got rock mechanics at the basis of all of this. So let's switch directions slightly here. Relevant factors for mining. On Earth, we've got a unidirectional, fairly strong, constant gravity vector. We've got a relative scarcity of energy, and I know that could be discussed. There's a mass abundance in comparison to off Earth, because we don't have to launch, we usually don't have as much difficulty moving large masses on Earth as we do getting large masses from Earth off it. Thick nitrogen atmosphere with an oxygen minor component. Now, it's not so minor for us, but if you're looking just at the amounts, it's minor. Difficult deposit access, and that basically refers to the fact that most of our deposits we can access only from one side. We can't really get to them easily from the sides, or certainly from the bottom. But to skip over a bit, when we get over to asteroids, we can actually access those, depending on what is our target material, from top, bottom, and sides. And that actually could revolutionize some of the exploration that we can do. And various other factors that are different on Earth, on asteroids, the moon, and Mars, of course, gravity and vacuum and so forth, that or near vacuum, are familiar, so I'm not going to spend a lot of time, but just the composition of the atmospheres. We think of Mars and Venus, although it's not up here, as having carbon dioxide atmospheres, which they do when you look only at the amounts of gaseous components. But it may not be the carbon dioxide that is ultimately of most value from a resource point of view. At the moment, it is, because we know what we know, and we can only work with that. As we get more experience, we may be able to find some trace components that could be really valuable for what we need. And for atmospheres, I think I'm not going to spend as much time on this as I wanted to, but it's comparison of the 4 main terrestrial planets. Of course, the Earth's moon could be considered one as well. You notice the temperature rows up there. Those are the differences between the temperature of the body as a black body radiator with no atmosphere, and the observed temperature, which shows the buffering and other thermal modifications to that black body temperature that are caused by a gaseous layer. Venus's atmospheric pressure is significantly higher than that of Earth, and of course Earth is much higher than Mars and Mercury and the Moon. These will all have effects on the behavior of the rock. Temperatures, this is a picture of Stickney crater on Phobos, the largest moon on Mars, and we can see just the effects of having no atmosphere. When you're in direct sunlight, you get a temperature of 25 degrees Fahrenheit. Partial shade, it's 100 or minus 100 in nearly full shade. It's minus 170 F. It's going to have some effect on what equipment you can use, which would include the bags, if you're going to bag this thing, although Phobos is a little large. But gravity gradients, which we also call slopes or hillsides. When you've got an odd-shaped body like these asteroids, Eros and Tutatis are both near-Earth asteroids, and the colors indicate the degree of slope with respect to the mass distribution to varying degrees of precision. Red is a steeper slope, and the cooler colors are the lower slopes, and they wouldn't necessarily map with what we would expect. So if these were solid and you could trundle along with some microgravity magic machine, something that looks steep might not be, and something that doesn't look steep might cause your rover to tumble. Okay, onward we go. Structural instability. We have pictures of bodies that are breaking up now, so we know what happens. And also you notice this line up here, that bodies that are bigger than very few 2 kilometers or so in diameter, if they spin fast, they actually break up. So we've got a size distribution. Down here, we actually have some fast spinners. Those are probably more or less solid rocks. So we deal with those differently than the ones that are rubble piles, which are at least covered with rubble, which is up in here, and a lot of these down here. Okay. Navigational difficulties. Tautatis also rotates in a chaotic manner. So it's going to be very difficult to basically be near it. Access issues. Orbital dynamics is not an easy thing. You don't just say, oh, there's the asteroid I want, aim it right up there. It's a lot more complicated than that. No. Aerospace engineering does not teach mining, but mining does not teach aerospace engineering either. So we both have things to learn from each other. Deposit formation, I've kind of covered this a little bit, but mineral deposits basically form whenever natural processes concentrate the desired material. We've talked about part of this. The deposit characteristics do reflect the geologic history, and impact mechanics, which we are not that familiar with on Earth, are going to be important to know and to understand as they reflect the deposit structure and properties. Mining methods. The whole idea of a mining method is, well, first of all, recall the unit operations of mineral production, and I've got them in the next two slides, although I won't spend time on them. Their reasons for being are to obtain only the ore and leave behind only the waste. In other words, you want just ore and you don't want any waste with it, and you don't want to leave any ore behind. Obviously, you can't do that, either one for 100%. Handle both the ore and the waste as little as possible. The purpose of mining, or not the purpose, but what mining methods do, or part of making a mining method, is to select the right technology for these unit operations to suit the deposit and the desired production rate and whatever other constraints you have. Planetary unit operations, go through these quickly. Fragmentation and excavation. They should be familiar to most of you. Comminution, if needed. Some of the comminution has already been done, but probably not to the right size fraction. Separation, and we've heard some talks about that. There are lots of methods that could be applied in space. Transportation, of course, is between all these processing steps. And some or all of these may not be needed. These are actually developed for terrestrial use, and the unit operations we need in space may be somewhat different. Various mining method classifications, and I usually spend more time on this to an audience who's not familiar with mining. Selection criteria, this is an abbreviated list, but still covers a lot. And the illustration is just to show how complex deposits can be. Again, that's intended for people who are not familiar with mining and often believe that just a shovelful from anywhere is all you need. And maybe someday, but not yet. Outputs of mining method selection. Okay. The next few slides are just a few potential asteroid mining or processing methods and/or that I've pulled out of either my papers or a few other papers. It's by no means exhaustive, and this is here to, well, just to look at and think about. Spin caving, and I've got some papers we can talk offline since I'm not running out of time. Asteroid processing, basically a form of jigging where you still keep things rotating to get a little bit of force vector to the outside and then just shake them around a little bit. This is the newest one in the list. It's a potential method for mining water-rich carbonaceouschondrite asteroids or parent asteroids. And it's a variation on the old idea of bagging the asteroid and heating it up. And we've got a fellow who's got a fairly good handle on a way of concentrating the sunlight. But basically it would be heating up the asteroid that has been mentioned earlier. Carbonaceous generally tend to have a fairly high proportion of water. Now, it's generally not ice, or it doesn't have to be ice. It's often water of hydration, water that's bound in minerals, and it might not even be water, it could be OH. So that would require a little higher temperature than might otherwise. And maybe for larger bodies, we'd also need to break them up so it doesn't take forever for the gases to come out of the inside. Planetary regolith mining has been proposed many times, and I expect will be fairly useful in various different places. Drag scrapers and also larger operations here. And another approach. Okay, the summary. The rock mechanics of a deposit reflects the deposit history, the deposit composition, and it's one of several but an important control of mining method selection. Mining has the same goals wherever it happens, whether it's the Earth or this part of the solar system or the outer part of the solar system, the Oort cloud, which has mass that dwarfs the entire rest of the mass of the planets in the solar system. But the whole idea is to obtain the desired material at the lowest cost. Now, cost is not necessarily dollars. It may be energy. It may be time. Just because we think of profit here on Earth doesn't mean that's how we're going to always be doing it. Mining methods in space, though, must start from the terrestrial experience, because by some measures we've been doing this for roughly 300,000 years, digging things out of the dirt to use. But it will also have to be adapted for the space environment. That's what I mean when I say that mining engineering and aerospace engineering and chemical engineering and several other engineerings and sciences do need to start working together, and what comes out will actually be a hybrid. It won't be mining and it won't be aerospace. In fact, I tease my aerospace friends that, they go down to the surface, we go up to the surface. And so there are other differences beside that. But what comes out is going to be a hybrid of this, not one or the other. It'll be something completely new. Now, this is what I want to leave you with is, we've got some more questions. A fellow named Bob Hazen has proposed that life drives mineral evolution. Does mineral evolution exist? If so, could it change the rock mechanics of space? Are the rocks in space different? Is basalt in space different from basalt on Earth, even though it seems to have the same mineralogy? How will familiar concepts of ductility versus brittleness change in space? How about granular mechanics without gases adsorbed on each of the little particles? And eventually, what's developed in space will come back and be adapted to Earth again for things like extremely deep mining to the mantle and the core. If something we find in asteroids that are pieces of cores, for example, turns out to be really cool. Anyway, there's a lot more, but I think I'm going to be getting the hook here in a minute. So thank you.
Thanks, Leslie, for filling our head full of rocks. That was awesome. Do we have one question? Is how much time we've got? Anyone got a question for Leslie? I had a question which was ductile versus brittle behavior, this idea of how do you think things like rocks are going to behave in zero gravity compared to Earth? Can you give us an example?
Probably the biggest thing that comes to my mind is things that are ductile on Earth, like mass copper and ice, may be a little more amenable to chipping in a brittle fashion, which is great because the ways we figured out how to break rock rely on its brittleness. So that may actually make some aspects of breaking up rock easier, or ice.
Terrific. Thank you very much, Leslie.